Ever stop to think about all that invisible logic that's just humming away inside
You
everything?
mean like in our phones and computers?
Exactly. Phones, factory robots, you name it. It's all run by these tiny electronic brains. And today, we're going deep. We're looking at two foundational technologies, TTL and CMOS.
Ah, right. Transistor logic and complementary metal oxide semiconductor. The bedrock, really.
So these are kind of the languages our devices speak.
Yeah, you could say that. They let electronics process information using just ones and zeros. Binary.
And they do that using logic gates, things like A and D or not T.
Precisely. Those gates are like mini decision makers. They take binary inputs, apply a rule, and give a binary output. The sources we looked at really break down how TTL and CMOS work, their differences, and even touch on other logic families too.
Okay, so our mission today, really get a handle on TTL versus CMOS. Why pick one? What's the bigger picture? Let's start with those logic gates. What are they actually doing inside the chip?
Well, at their core, these logic ICs, the chips, they're packed with tiny components, mostly transistors these days.
Transistors, right, and resistors. Diodes sometimes.
Yeah, though modern stuff heavily relies on MOSFETs, which is, a CMOS thing. But their main job, making sensible decisions. Yes or no.
Based on those binary inputs. True, false, 10.
Exactly. They perform Boolean algebra. It sounds fancy, but it's just applying logical rules to get an output. That's how complex calculations happen, from these tiny steps.
Tiny components, sensible decisions. Still sounds a bit like magic. And I remember reading there's a physical limit, right? You can only cram so many onto one chip.
Oh, absolutely. And shrinking them down has been, well, a massive driver of progress.
How so?
Well, by fitting more logic gates onto that little piece of silicon, you get huge jumps in performance, more features, and critically, better power efficiency.
Right, right. More brain power, less energy needed. Makes total sense. Okay, so let's zoom in on TTL first. What's its story?
TTL, transistor logic. It's built using bipolar junction transistors, BJTs. You hear about NPN or PNP types.
Okay.
And what's interesting with TTL is that these transistors, they handle both the logic part, the decision, and they amplify the signal.
Wait, they do both? How does that work?
Well, basically, the voltage you put on the base of the transistor, that controls the current flow between the other two parts, the collector and emitter.
So it's like an on-off switch.
Pretty much.
Hmm.
That switching action creates the 1 euro logic output.
Yeah.
And like one source mentioned, a small input current can control a much larger output current, so you
Wow.
get that amplification built in.
Got it. Double duty transistors. No, I think I read TTL was big in older computers. Is it still around much?
Yeah, historically it was huge, really dominated early computer design. But for building the actual IC chips we use now, CMOS has largely, well, taken over.
So TTL is more of a legacy thing now.
You might find it in some specific niches, maybe older industrial stuff, but yeah, CMOS is the main player for chips today.
Okay, perfect segue to CMOS then. What makes it the go-to choice now?
CMOS, complementary metal oxide semiconductor, is everywhere. Microprocessors, RAM, SRAM, ROM, EEPROM, even simple logic gates like inverters. It powers most modern digital stuff.
And that name, complementary, what's that about?
Ah, that's the clever part. It uses two types of MOSFETs, metal oxide semiconductor, field effect transistors,
Yeah.
a P-type and an N-type.
Okay, two types.
So the complementary magic is that only one type is conducting electricity at any given moment. The other one's off.
So one's always idle.
Exactly. And that's the key to its incredibly low power consumption. It's like a switch that's almost always off unless it absolutely needs to be on. Huge power saver.
Okay, that's the secret sauce for power efficiency.
Yeah.
Makes sense. Any other big advantages?
Oh yeah, CMOS gives you a great mix. It's relatively fast, uses very little power, and it's got really good noise immunity. It doesn't get easily upset by stray electrical signals.
Noise immunity, right. That sounds important.
It is, especially in electrically noisy places. Plus, CMOS can work over a wider range of voltages. And of course, the miniaturization has been incredible. We can now put billions, literally billions of these transistors on one chip.
Billions. Wow, that's just hard to wrap your head around. And I guess that low power use is why your phones last as long as they do. Well, sort of long.
Huh, yeah, sort of. But seriously, for anything battery-powered, CMOS is king. Longer battery life, less heat generated, massive wins for portable devices.
Okay, the picture's getting clearer. Let's put them head to head. Performance-wise, TTL versus CMOS, what are the main trade-offs?
Okay, performance. CMOS generally wins on low power, like we said, big advantage. It also has better noise immunity and higher fan-out.
Get fanned out. What's that again?
Fan-out is basically how many other logic gate inputs one gate's output can successfully drive or talk to.
Got it. So CMOS can talk to more gates. What about TTL's strength?
TTL, well, historically it could offer faster switching speeds. That was its edge, especially for high-frequency stuff. But it has higher input capacitance, which can sometimes slow things down, and it's more sensitive to static electricity. Needs careful handling.
ESD sensitive. Right. So CMOS is generally tougher and uses less power, but TTL could be faster in some very specific cases.
That's a fair summary, yeah. Though modern CMOS is very fast too. But what about cost? Is there a difference there?
Good question. Cost.
Yeah. Generally, CMOS components tend to be a bit more expensive than the equivalent TTL ones. All that advanced tech costs a bit more to make.
So if you're building something simpler or really watching the budget.
TTL might still be a more cost-effective choice in some situations, yes.
Okay, interesting. Performance versus cost. Now, where do we actually find these being used, like typical applications?
CMOS is, well, everywhere. Amplifiers, microprocessors, the brains in computers, image sensors and cameras, analog to digital converters, communication chips and phones, fast memory like SRAM. The list is huge.
Okay, so CMOS is the default for most complex modern stuff. What about TTL? Where does it still pop up?
You might still see TTL in some industrial control systems, maybe older digital watches or calculators, certain types of test instruments, sensor interfaces, actuators, even some music synthesizers used it. More niche stuff generally.
So it sounds like the choice really depends entirely on the job. How does an engineer decide TTL or CMOS for a new design?
It's a balancing act. You have to look at the specific needs. What voltage does it need to run at? How much electrical noise is expected? That's the noise margin we mentioned.
Right. Speed requirements too, I guess, and cost?
Absolutely. Speed, cost, power budget.
Yeah.
TTL usually runs at a fixed 5 volts and uses more power. CMOS is more flexible with voltage and has that great noise immunity, which is really valuable in, say, a factory setting.
Okay. So if you need top performance, low power, good noise rejection, CMOS seems like the way to go.
Generally, yes. That covers a lot of modern needs.
But if maybe speed is the absolute top priority for a simpler task and cost is tight, maybe TTL could still be considered.
It could be, yeah. It really just boils down to what the application demands. That dictates the logic family choice.
Now, you hinted earlier, TTL and CMOS aren't the only game in town, right? There are other logic families.
Oh, definitely. We can broadly classify them based on the type of transistor used.
Yeah.
You have bipolar families and unipolar or MOS families.
Okay. Bipolar includes TTL.
Yes. Bipolar is split into saturated logic that includes things like RTL, DTL, and TTL, and non-saturated logic like ECL and Schottky TTL.
ECL, I think you mentioned that one, and unipolar.
Unipolar or MOS logic has its own branches. NOS, PMOS, and of course CMOS, which cleverly combines N-channel and P-channel MOS types.
And all these different families have different pros and cons.
Exactly. Different speeds, different power consumption levels, different noise immunity, different fan-out capabilities. It's all trade-offs.
You said ECL is the fastest. What's the catch?
Yeah, emitter-coupled logic, ECL, is incredibly fast.
Yeah.
But the catch is power consumption. It uses a lot of juice.
Ah, okay. Speed costs power. Makes sense. You also mentioned things like logic levels and noise margin before.
Right, logic levels are just the specific voltage ranges that count as a 0 low or a 1 high. And the noise margin is that crucial buffer zone. It prevents noise from accidentally flipping a state. Vital for reliability.
And there were thresholds too, and something about a Z state?
Yeah, input and output thresholds
Let me
define
look.
the exact voltage where the input switches. And the high impedance state, or Z state, is used in tri-state logic. It basically lets you electrically disconnect an output from the bus it's connected to. Very useful.
This is getting quite technical. Are there specific numbers or parameters engineers use to compare these families directly, like metrics?
Yes, absolutely. There are key parameters. One big one is propagation delay, TPD.
Okay, what's that?
It's the time lag. How long it takes for the output to change after the input changes. Usually split into TPLH, low to high, and TPHL, high to low. Lower delay means faster operation.
Faster is usually better. Got it. What else?
Power dissipation, PD. Simply how much power the gate uses. Lower is better for efficiency, right? You've got static dissipation power used when it's just sitting there, and dynamic dissipation power used when it's switching.
Okay, power use. Makes sense.
Then there's the power delay product, BDP. You multiply the propagation delay by the power dissipation.
So, speed times power.
Kind of, yeah.
Yeah.
It's a figure of merit, a way to gauge overall efficiency.
Yeah.
Well, lower PDP is generally better. You're getting good speed without excessive power draw.
Like good miles per gallon in a fast car.
Exactly like that.
Yeah.
Then you have fan in, just the number of inputs a gate has, and fan out, which we talked about how many other inputs one output can drive reliably.
Hmm.
That depends on output currents, IOH and IOL,
Hmm.
and input current needs, IH and IO.
Right. How many things it can talk to. And noise margin again.
Yep, noise margin,
Yeah.
NM. We calculate NMH for the high state and NML for the low state. It tells you how much noise voltage it can handle before things go wrong. Higher margin means it's more robust.
Okay, so delay, power, efficiency product, if fan in out, noise margin, anything else major.
Well, there's also the overall operating speed, sometimes called switching speed. Noise immunity, which is related to noise margin, but sort of the overall concept. The operating temperature range, the specific logic voltage levels themselves, VIH, VIL, VOH, VOL, and the actual input and output currents, IIH, ILA, IOH, IOL.
Wow, okay. That's a lot of factors to juggle when choosing.
It is. Engineers use these parameters to compare families and select the best fit for the specific application's constraints and requirements.
Seems like a complex balancing act. Now, thinking about modern tech, are we still just talking TTL and CMOS, or are there newer trends?
Well, TTL and CMOS are still fundamental, but yeah, things have evolved.
Mm-hmm.
A big trend is programmable logic devices, PLDs, especially FPGAs.
FPGAs, field programmable gate arrays.
Exactly. These are amazing chips because you can configure and even reconfigure their internal logic after they're manufactured.
Really, you can change the hardware design after it's built.
Essentially, yes. You program them to implement whatever complex logic function you need. You can even create custom hardware accelerators. It's incredibly flexible.
Reconfigurable hardware.
Wow, that sounds powerful.
It really is. FPGAs give designers huge adaptability. They're used in everything from aerospace and high-speed trading systems to complex robotics and custom embedded devices.
Okay, well, this has certainly been a fascinating deep dive into the digital logic world. So just to recap the main thread, TTL offered speed, historically, but used more power and was less robust against noise.
Right, while CMOS came along and really excelled in low power consumption and high noise immunity, making it dominant today.
Perfect. And choosing between them, or any logic family really, is all about trade-offs, isn't it? Balancing speed, power, cost, noise immunity, based on what the specific job needs.
Precisely. There's rarely one best answer for everything. It always depends on the application's priorities.
So it makes you wonder, doesn't it? As technology keeps pushing forward, how will future logic families tackle these trade-offs? Can we get even faster and more power efficient? And what completely new things might that enable?
That's the billion-dollar question, isn't it? It really is. Maybe something for you, our listener, to think about. You probably see that power versus performance tension in your own gadgets every day. Perhaps you might want to look into some specific uses of TTL or CMOS that interest you, maybe how they work in industrial automation, or what's really going on inside that battery sipping device you rely on. Thanks for joining us for this deep dive.